Hello everyone. In this video, we will be seeing about the relationship between signal energy, its vector and Euclidean distance. So here, we will understand the fundamental relationship between the signal energy, vector representation and the Euclidean distance in context of digital communication system. So the signal energy and the vector representation of the signals we will be seeing, and also the Euclidean distance with respect to the digital communication system, and we will delve into how the signals can be represented as vectors in a signal space, and how the energy of the signal will relate this to the length of its corresponding vector, and how the Euclidean distance will provide a measure of dissimilarity between the signals, which is important or crucial for the reliable detection of the receiver. So the energy of the signal, it is a measure of its strength or magnitude over time, and for a continuous time signal, that is SI of t, the energy can be defined as EI is equal to integration from 0 to capital T SI square of t dt. So in digital communication systems, the signals represents the symbols of bits of information, and higher energy signals are generally more robust to noise and interference, which will lead to improved reliability. So here, this is the equation for the energy of the signal. Now, here we'll be using the representation of the signal as SI of t is equal to summation j is equal to 1 to capital N Sij phi j of t dt. So this will be substituting in the equation for energy. Now, when we use this equation in the equation for energy of the signal, we get EI is equal to integration 0 to capital T, as this is a square, SI square of t dt. We have to write this equation twice. So what we'll do is, for the first equation, we will take the summation as from j is equal to 1 to capital N Sij phi j of t dt. Then in the second summation, we'll be taking it as summation k is equal to 1 to capital N Si of k phi k of t dt. Now, as here we have Si square, so we need to write the summation two times, and in the first summation we have taken the summation from j, and in the second summation we have taken the summation from k. So here we are using two different notations, that is, in the first it is j, and this j it is changed to k in the second equation. So instead of j, here we are taking k. So we have taken two variables to represent the summation, that is j and k. Now we will rearrange this equation. When we rearrange this equation, we get EI is equal to summation j is equal to 1 to n, then summation k is equal to 1 to n Sij Sik integration 0 to capital T phi j of t and phi k of t dt. Okay, so this we will take it as equation 1. Now we know that integration from 0 to capital T phi j of t into phi k of t dt, it is 1 when j is equal to k, and it will be 0 when j is not equal to k. So when j is equal to k in equation 1, okay, when j is equal to k, what we'll get? When j is equal to k, we are getting the value for this equation as 1. So we'll substitute this in equation 1. So here this will become 1. Okay, because when j is equal to k, integration from 0 to capital T phi j of t into phi k of t dt will be 1. Substitute this in equation 1. We get EI is equal to summation j is equal to 1 to n, summation k is equal to 1 to n Sij, okay, into Sik, and this term will become 1. So this is what we get the energy of signal when j is equal to k. Now the second condition is when j is not equal to k, it will be 0. So when j is not equal to k, this part of the equation will become 0. So we get EI is equal to 0, because if you substitute here this part as 0, this whole RHS will become 0 for equation number 1. Therefore, EI will be equal to 0 for J not equal to K. Okay. So, here from this we can write that energy of the signal, it can be written as EI is equal to summation J is equal to 1 to N, summation K is equal to 1 to N, Sij into Sik for J is equal to K. Okay. So now here you can see you have two summations. Okay. We will make it as only one summation because both the summations are same here. So we can write here EI is equal to summation J is equal to 1 to N Sij square. Okay. So here we'll take this as equation number 2. Now, as summation J is equal to 1 to N Sij square, it can be written as Si square within the double lines, which will indicate the length of the signal vector. So this will take it as equation number 3. Okay, this indicates the length of the signal vector. Now here by comparing equation 2 and 3, we can write that EI is equal to what? It is equal to the length of the vector whole square. Yes, no? Because here RHS and this LHS are same. So this EI will be equal to square length of the signal vector. So we can write this as EI is equal to SI whole square, that is double line whole square. So this is the relation between the signal energy and its square length of the signal vector. Okay. Now we know that here we know that this square length of the signal vector, it is equal to SI transpose into SI. Okay, so this energy of the signal, this can be written as EI is equal to SI transpose into SI. Okay, so now next we'll see what is the Euclidean distance. Okay, one more thing here is if you want the reliable communication, then you have to choose the optimal signal energy. That is, if the energy is higher, then it will ensure that is the energy of the signal is high, it will ensure the robustness and the reliability. If the signal energy is very low, then it will be susceptible to noise and the interference. Okay. Now we will see about the Euclidean distance. So Euclidean distance in the digital communication, it is a measure of dissimilarity between the two signals. So given two signals with the corresponding vector representation, then Euclidean distance, here it is given by this equation. Okay, that is di of k is equal to this again double lined square of Si minus Sk. So this will represent what? It represents the signal square length of the signal vector. Okay. Now here we'll see about what is the Euclidean distance. So in digital communication system, the Euclidean distance between the signal vector, it is a crucial parameter. That is, it is an important parameter for designing the optimal detectors. That is, the receiver's task is to determine which signal was transmitted based on the received signal and which is the transmitted signal corrupted by the noise. So a common strategy is to choose the signal vector that is closest, okay, to the received signal vector in terms of the Euclidean distance. And the probability of error in detecting the correct signal, it is inversely related to the Euclidean distance between the two signal vectors. So this was about the Euclidean distance. Now we will see the derivation of this. Okay, so here Euclidean distance, how it is given, it is calculated between the two signal vectors, and it can be given by dik is equal to this double line square Si minus Sk. Okay, so this dik, it is nothing but the distance between Si and Sk. Now we know that this, it can be written as, that is Si minus Sk double line square, it can be written as summation j is equal to 1 to n Sij minus Skj square. Okay, and we'll take this as equation number 2, and this is the equation number 1. And we know that the energy of the signal, it can be given as integration. It is from 0 to capital T Si square of t dt, that will be equal to again the square length of the signal vector, and we'll take this as equation number 3. Now we will substitute equation number 3 in equation number 2, so that we get equation number 2 as Si minus Sk square. Okay, that is the square length of the difference between these two signal vectors, that is Si minus Sk. It can be written as integration from 0 to t. Okay, and Si of t minus Sk of t whole square dt. We'll take this as equation number 4. Okay, now so this equation number 4, it is nothing but the Euclidean distance between two signal vectors, that is Si and Sk. Now we need to calculate the angle between the two signal vectors, so which is given by cos of theta ik is equal to transpose of Si into Sk divided by, this is the signal vector of Si and signal vector of Sk. We'll take this as equation number 5. Now when we make the numerator of this equation as 0, okay, that is transpose of Si into Sk, when we take when we make this as 0, what will be getting? We'll be getting cos of theta ik is equal to 0, as we have made the numerator as 0. So equation 5 will be cos theta of ik is equal to 0. So here the two signals, these are said to be orthogonal or perpendicular to each other, okay, when theta of ik is equal to 90 degrees. Yes, no? So when theta of ik is 90 degrees, cos 90 will be 0. Okay, so here when the two vectors are orthogonal to each other, the angle between them will be 90 degrees. Fine. So we have calculated the Euclidean distance, and also we have calculated the angle. Okay, so here in the first part, just a minute, here in the first part, here in the representation of the energy signal, okay, we have shown that the length is unity. Okay, yes, no, just a minute. Okay, so here we have calculated the Euclidean distance, and as well as we have calculated the angle. Okay, so we'll summarize this, what we have done here. The signal energy, that is the energy of a signal, it is equal to the squared Euclidean norm. Okay, that is the length of the vector representation. Okay, that is this one. Okay, this one, squared Euclidean norm. Okay, this is usually these double lines are called as norm. So length of the vector representation, and and the Euclidean distance and that is the relationship between the Euclidean distance and the signal similarity. Here we can say that the Euclidean distance, it quantifies the dissimilarity, or it measures the dissimilarity between the signals and the vectors, and the Euclidean that is the relationship between the Euclidean distance and the detection performance. There we can say that the larger Euclidean distances between the signal vectors lead to lower probabilities of error in the detection. So understanding these relationships, it is a fundamental like concept to design efficient, reliable digital communication system. And by carefully choosing the signal constellations with large minimum Euclidean distances and ensuring sufficient signal energy, we can minimize the impact of noise and interference and achieve robust communication. Okay, hope you have enjoyed the video and understood. If you have any doubts, you can message or you can write in the comment section. Thank you.